Today we will also discuss one important theorem related to measure theory. Okay, now start about Lebesgue Monotone Convergence theorem. Okay, we first write the statement of this Lebesgue Monotone Convergence theorem. We write here, let X a mu be a measurable space and E be a measurable set in X, and if e to 0 plus infinity close be a measurable function, be a measurable function, and if n be a sequence of 0 plus infinity, okay, valued measurable function, sequence of 0 plus infinity valued measurable functions. Okay, then measurable functions on E such that if n less than equal to if n plus 1, okay, for all n belongs to natural number, and if n tending to f, then what happened? Then limit n tending to infinity e f n d mu equal to integration of e f d mu. Okay, now we write, just X algebra mu be a measurable space and E be a measurable set in X, and if e to 0 in plus infinity be a measurable function, and fn be a sequence of 0 plus infinity valued measurable functions on E such that fn less than equal to fn plus 1 for all n belongs to n, and fn converts to f. Then what happened? Then limit n tending to infinity e fn d mu equal to e f d mu equal to what? Equal to integration e limit n tending to infinity fn d mu. Okay, we also prove this important theorem. Okay, we'll start this proof now. So what is given? Just fn less than equal to fn plus 1. Okay, for all n belongs to n, this one is given. This means that we have f1 less than equal to f2 less than equal to f3 less than equal to less than equal to fn less than equal to fn plus 1 less than equal to and less than equal to f, since fn converts to f. Okay, we write here, since fn converts to f. Okay, then what happened? We erase our portion and going to discussion about that. Okay, now here we write, hence what happened? Hence integration of e f1 d mu less than equal to integration of e f2 d mu less than less than equal to integration of e f n d mu less than dot 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 less than equal to integration of e f d mu. Okay, then what happened? So the sequence this one integration of e f d mu f n d mu. Okay, v monotonically increasing sequence, v monotonically increasing sequence. Okay, hence limit n tending to infinity integration of e f n d mu exists, and integration of e f n d mu less than equal to integration of e f d mu for all n belongs to this natural number. Then what happened? What we get here? We get so simple event. So we get limit n tending to infinity integration e f n d mu less than equal to integration of e f d mu. We mark this one. Okay, now note that here we write integration of e f d mu equal to what? Equal to supremum of psi belongs to s plus 0 less than equal to psi less than equal to f integration of e psi d mu. Let psi belongs to s plus and alpha belongs to 0 1 open, and define en equal to this one. X belongs to e such that fn x greater than alpha psi x. Okay, then what happened? So simply we get en, then some, that means following property of en we follow. Okay, but we write it later. First we erase that portion and we're going to further discussion of that. Okay, then we erase that portion and going to further discussion of that. We define just en and write here some certain property of en. Okay, now we just move and going to discussion of certain property of en. Okay, now we just write here. Note that first one, en be measurable, en be measurable. Second one, En is monotonically increasing. En be monotonically increasing. Now note that En subset of En plus 1. This implies that limit n tending to infinity En equal to union of n equal to 1 to infinity En equal to E. Okay, now alpha psi x less than equal to fn x. Okay, for all x belongs to En. Okay, this implies that alpha integration of En psi x dx less than equal to integration of En fn x dx. Okay, oh sorry, not dx, here we write d mu, then this one is beta. Okay, because we integrate with respect to mu. Okay, we integrate with respect to mu, then this one is beta. Now we're going to discussion of that. This one less than equal to obviously E fn x d mu. Okay, taking limit as n tending to infinity, taking limit as n tending to infinity, here alpha integration of E psi d mu less than equal to limit n tending to infinity E fn x d mu. Okay, or fn d mu. Okay, then if for alpha equal to 1, for alpha tends to 1, we get integration E psi d mu less than equal to limit n tending to infinity integration of E fn d mu. Okay, then what we get, here we write, we're taking supremum in both sides, taking supremum into both sides, we get what we get. Okay, it is our portion and going to further discussion of that. The supremum of integration E psi d mu, okay, less than equal to limit n tending to infinity integration of E fn d mu. Okay, this implies that integration of E f d mu less than equal to limit n tending to infinity integration of E f n d mu we marked as 2. Hence from 1 and 2 we get, from 1 and 2 we get limit n tending to infinity integration of e f n d mu equal to integration of e f d mu. Now we obviously write some corollary. Okay, we write corollary. That means we also prove these portions. We write corollary now. Here, let x a mu be a measurable space. Be a measurable space, and E be a measurable set. Be a measurable set in X if E2 0 plus infinity be a measurable function. Be a measurable function and psi n be a sequence of 0 plus infinity valued simple functions. Valued simple functions on E such that psi n less than equal to psi n plus 1. Psi n less than equal to psi n plus 1 for all n belongs to n, and psi n tends to f. Then what happened? Then limit n tending to infinity integration e psi n d mu equal to integration of e f d mu. Okay, that means we write this corollary now. Just psi and one simple functions. Okay, this one obviously satisfied this monotone property and obviously converges to f. Then limit n tending to infinity integration of psi n with respect to mu obviously here equal to limit n to integration of limit n tending to infinity psi n d mu. That means limit integration of f d mu. Okay, this one is the corollary of Lebesgue monotone convergence theorem. Okay, one of the important theorem. We just prove it too easily. Okay, just we use monotonicity property and again we construct some en and then we done this proof of Lebesgue monotone convergence theorem. Okay, there is not a problem at all, so easily we done it. Okay, so easily we done it. En construct and then converse part also done. En measurable and en monotonically increasing. In this way this property used, we also done this one. Okay, so now it is that portion and going to an important lemma, which lemma also plays many innovations in measure theory. This we also discuss this lemma now. This one is Fatou lemma, an important lemma proved by some mathematician, Fatou I think, and in his name this lemma is, that means Fatou lemma. Okay, Fatou lemma. Let X a mu B measurable space, B measurable space, and let E belongs to this A. Okay, and if n be a sequence, and if n be a sequence of 0 plus infinity valued measurable functions, valued measurable functions, then what happened? Then limit n tending to infinity, okay, infimum of fn d mu integration with respect to e equal to, that means less than equal to limit infimum of n tending to infinity integration of e fn d mu. Okay, we have to prove this. Okay, now we write here proof. Now we write here for n belongs to this natural number, define Gn x equal to infimum of fn x fn plus 1 dot 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 fn plus 2 dot 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 this one. Then first one is Gn be measurable, be measurable, and second one, okay, g1 less than equal to g2 less than equal to dot 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 gn less than equal to gn plus 1 less than equal to dot dot dot. Okay, that is gn be monotonically increasing, be monotonically increasing. Then we write here, okay, what we write, we also construct this gn, then is gn be measurable, since fn be measurable, and obviously gn is monotonically increasing. Okay, then we write here by definition of gn we get gn less than equal to fn for all n belongs to n. Okay, this implies gnx less than equal to fnx for all x belongs to e. Now erase that portion and going to further discussion of that. Okay. Then taking limit infimum and tending to infinity, we get what? We get so simply this one, limit infimum of n tending to infinity. Okay, infimum of the e here cn d mu less than equal to limit infimum of n tending to infinity fn d mu with respect to e. We marked as this one is 1. Okay, then again we write here this one, that means gn that means we also write we have limit n tending to infinity cn x equal to what? Limit n tending to infinity infimum of fn x. Okay, since gn is monotonically increasing, since gn is monotonically increasing and limit n tending to infinity gn equal to limit infimum n tending to infinity fn. Okay, then what happened? Then limit n tending to infinity integration of e gn d mu equal to integration of e limit n tending to infinity gn d mu. Okay, equal to what? Equal to e limit infimum of fn n tending to infinity d mu. Okay, so this one is because this one happened. Why? Because this one is performed monotonically increase, that means from Lebesgue Monotone Convergence theorem. Okay, this one happened, so this one means this one. Okay, so we write here by Lebesgue, okay, monotone convergence theorem. Okay, hence we marked it, this one is 2. Then from 1 and 2 what we get? Okay, from 1 and 2 we get limit n tending to infinity e gn d mu less than equal to limit infimum of n tending to infinity e fn d mu. Okay, now it is our portion. I'm going to further discussion of that. this one is the required result. Okay, that means integration of e limit n tending to infinity fn infimum of fn d mu less than equal to limit infimum of n tending to infinity integration of e fn d mu. Okay, then we also prove this Fatou lemma, one important lemma in measure theory. Okay, we just prove it by construct some gn. Okay, with some gn, then gn satisfies, gn is a measurable function, and gn monotone, gn satisfies the monotone convergence theorem. Okay, then we get this result, and then then we also show this one. Okay, so simply we also show this one. Okay, then today we stop here. Okay.